Uh, Thank you very much for the very kind introduction and the invitation for being a part of this conference and giving this talk. Please give me one moment. Let me just share my screen and we'll get started. Okay, good morning again. Am I audible, visible, and is my screen visible? Someone can confirm. Okay. Great. Thank you again for the invitation and the kind introduction. It's my honor and privilege to be a part of this conference and also perhaps start off proceedings as the first speaker. I do wish all the organizers all success for the conference, and I hope it turns out to be a very productive event. So the topic for my talk today is causality in explainable AI, and talk about the motivation, methods, and some of our recent efforts in this direction. Please do feel free to interject and ask questions at any point. I did log in from another device just so I can see any questions, because once I start sharing my screen, I may not be able to see what's here, but I've logged in from another device and I should be able to see. Just a minute. Okay, so if you post questions, I'll be happy to look at it on the other device. And I also know that I mean, the audience is perhaps a mix in terms of backgrounds in math, data science, computer science. So I hope that this will be of interest to most of you in the audience here. I personally believe, as a person with a background in math myself, I think I personally believe machine learning and AI data science has a very nice intersection between theory and application. Right? It allows a spectrum of topics to study, from theoretical aspects of machine learning and AI all the way to the applied side, where people see deployment of machine learning and AI models. I believe that causality in explainable AI is one such which has very strong mathematical underpinnings, but perhaps has important repercussions in real world practice. Let me first start off by trying to demystify the terms that we have in the title, explainable AI. Right? So all of us, I'm quite sure, are aware of AI, data science, machine learning. Explainability in AI has received a lot of attention in the recent past. One moment, let me just see if I can. Sorry, just trying to get a pen. Okay, here we go. Okay, yeah. Explainable AI has received a lot of attention in the recent past, primarily because as machine learning gets deployed in more and more risk-sensitive and safety-critical applications, it becomes very important for these models to explain their decisions. European Union has now a formal clause as part of its General Data Protection Regulation that states that a business that uses personal data for automated processing must be able to explain how the system makes decisions, which means if a bank is using a machine learning model to decide whether a customer should get a loan, if a customer comes back and asks, why was my loan declined? The model should be able to explain why. Right? So similarly, US actually has several such legislations, one of which is called the Algorithmic Accountability Act of 2019, which again requires companies to provide an assessment of risks posed by automated decision systems. More generally speaking, there has always been a right, a fundamental right, like how we have many fundamental rights across people in the world. There's also a fundamental right to explanation, which was largely not invoked in the context of AI and machine learning, but more generally speaking for decisions across the world. And it's becoming important to consider that right in the context of machine learning and AI models. In India, Niti Aayog has an entire responsible AI strategy document available publicly. If you search for Niti Aayog responsible AI, you'll see a two-part document that lists several aspects of responsible AI that needs to be considered as we move along as a technology savvy country. And a very, very important component of it is explainability, transparency, and accountability of AI machine learning models. Right, one thing is, you could say all this seems esoteric. It probably matters for Western countries like Europe and America. Why should we bother about it, right? So we're still a developing nation at this point in time. That's not really true, because let's say if you're a company like Infosys, CTS, TCS, any of the service companies, let's say you're developing a software for the bank in Germany, right? So then and you're using a machine learning model to make a decision based on a customer's input to decide whether to give a loan or not. Now, if the customer asks a query as to why my loan was declined, it's going to come back to us here to explain through our model as to why that decision was arrived at. So we are a very globally interlinked economy at this point in time. And a lot of machine learning models that we deploy as a country, be it in our own country, be it as a product that we deliver to the world, or be it as a service that we deliver to the world, it's extremely important to consider the explainability of AI/ML models in all of these deployments. So if this is this important, what are people around the world doing at this point? Right? So a large part of this requirement for explainability came only in the last few years. We all know that AI machine learning has probably changed the landscape of technology in general in the last decade or so. And only in the last few years, as these kinds of technologies started getting deployed in risk-sensitive settings, right? So if you look at where the success of machine learning is today, right? Look at where all you use machine learning in a given day, right? You probably use it in your spam filter, you use it on your Amazon or Big Basket or Flipkart purchase systems, you see it on your Netflix or Prime Video recommendations, you probably see it on Facebook face detection, you see it on your Apple Siri or Google Now or Microsoft Cortana speech recognition systems. These are the different places we see it. And in all of those places, if you notice, the risk of a bad decision is really low. I get a bad movie recommendation, okay, I lose 3 hours, right? Probably if I go to a theater and watch it, I lose 500 rupees, right? But that's not a life or a limb. On the other hand, if you actually had to deploy this in the cockpit of an aircraft, or maybe at the reception in a hospital to decide whom to screen and whom not to screen, now things start getting tricky, right? Because one wrong decision in the cockpit of an aircraft could lead to loss of many, many lives, right? Or one decision, let's say you were using machine learning based on seismic waves to predict earthquakes in a certain part of the country, then if something goes wrong there, it's a serious mishap in terms of how many people could get impacted and affected. Now, this is a serious consideration, right? So as AI and machine learning gets deployed in risk-sensitive and safety-critical applications, explainability, interpretability, accountability become very, very important. And over the last 4 or 5 years, researchers have looked at from multiple perspectives, from a core machine learning perspective, from a planning perspective, from a multi-agent system perspective, from a computer vision perspective, from a natural language processing perspective, from a robotics perspective, from a search perspective, so on and so forth, right? So different, depending on which application you're using AI, and these are different branches of AI after all. And depending on which branch you're using it in, explainability has been worked on. But if one had to ask the question, what do we really mean by explainability? Unfortunately, we still don't have an answer, right? It seems like to be the proverbial elephant in the room, or the proverbial 5 blind people looking at different parts of the elephant at this point in time, right? Depending on how a person views explainability, they see it as different things. For people who use the systems, one of them could be interested in knowing whether they can trust the AI model's decisions. A data scientist may be interested in knowing whether this was the best model ever built, so that an explanation could help them probably build a better model. An IT ops person could be interested in knowing how to debug this model. An auditor or a regulator or a government body could be interested in knowing whether these systems are actually fair in practice. And a customer support person could be just interested in knowing, how do I answer this customer complaint? right? So that's all they're interested in terms of the explanations that come out of these models. So different people, for different people, explainability could mean different things. And this also translates to a technical lack of understanding of what explainability really means. So today you have different ways of looking at explainability in AI and machine learning. One is whether an explanation should be global or local. Should you give an explanation for an entire data set, or do you give an explanation just for one single data point of a data set? Do you come up with an explainability method that works for all kinds of machine learning models, or you have to have a separate one for neural networks, a separate one for support vector machines, so on and so forth? Do you have an explainability model that does explanations post hoc? After you come up with a machine learning model, you add a layer of explainability to it, or do you come up with something that's where explanations are built into the system itself? And whether you have explanations to be actionable or not actionable, whether you have it at a feature level or a concept level, and the focus of today's talk, which is whether explanations are correlational or causal. Right? So I'll talk about a bit more of this as we go forward. So as you can see, each is right in its own way, which is perhaps the reason why we're still like blind people groping around an elephant to try to find out what does this really mean. Right? So that's one of the reasons why legislations around explainability, regulations around explainability of AI/ML models at deployment have still not been understood well enough, because we still have not objectively, precisely defined what explainability really means in mathematical terms. So in our group here at IIT Hyderabad, we've been looking at several aspects of this, which is what I'm going to try to talk about over the rest of the duration of this talk. Our overall theme in terms of our research is to work on deep learning, machine learning, computer vision. And we broadly work on performing organic lifelong learning of robust explainable models. So we'd like, rather than treat machine learning or AI to be a black box approach and a single box approach where you have some past data, you just learn from it and deploy it and you forget about it. That's perhaps the older way of doing things. How do you adapt to newer data coming in? How do you adapt when a data distribution changes over time? How do you ensure you can explain these models? All of this is something that we try to do in our group here at IIT Hyderabad. In terms of explainability itself, we have been looking both at post-hoc explainability and intrinsic explainability. In post-hoc explainability, we look at once you have built a machine learning model and you're in the process of deploying it. Now, how do you add a layer of explainability after you build a model? You've already deployed a model, you cannot touch it anymore, but you have to somehow explain the model based on some meta-analysis that you do on the model and the data. So that's the more popular approach. We've been doing some work in that direction. And in the intrinsic interpretability is the more challenging, but perhaps more rewarding one, where when you build a machine learning model itself, you try to see how do I ensure that this is inherently explainable, right? So that's perhaps the other direction that we've been looking at. And we've been publishing this work in several top-tier conferences around the world. But the part that I'd like to highlight here is the fact that among these methods, there are both non-causal methods and causal methods, right? So both have their own value in the system. And that's what I'll try to elucidate for the rest of the talk. One of our most salient efforts is called GradCam++. This is the work that we published in 2018, where the broad idea was to explain the decisions of convolutional neural networks, which are deep learning models for computer vision used to understand images and videos. We came up with a pixel level weighting strategy to compute gradients for explanations. We showed that you could get a simple analytical form for the solution and thereby be able to compute it efficiently. And this is one of our efforts that has been extensively used around the world today. It was used extensively during the COVID pandemic for explaining decisions of machine learning models on on chest X-ray images, finding defective cells in solar arrays, explaining cancer prediction on gene expression data, identification of pathogens in tomograms, so on and so forth. So this work has a reasonable amount of citations at this point. And if you're interested, the work is available on arXiv or GitHub. And you're more than welcome to look at it if you're interested in explainability for deep learning models on images and videos. But coming to the core topic of this talk, which is causality in explainable AI, there's a known fundamental difference between causation and correlation. And the kind of questions that we'd like to understand is Is feature correlation to output a true indicator of explainability? Or do we need to understand causal relationships in data output pairs? Let me probably explain that with an example. Suppose we have a machine learning model that we have deployed in a hospital to predict the risk of heart attack. Right? So I've collected thousands of patient data. I have now looked at who had a high risk for heart attack, who did not, and now I've developed a machine learning model that I have deployed to actually make it predict the risk of heart attack. Now, because I want explainability, it's a risk-sensitive application. Now, let's say for some person who gets a high risk for heart attack, I go try to ask the model, can you tell me why did you say the person has a high risk for heart attack? And the model says, go look at the patient's blood pressure, right? The blood pressure attribute of the patient record is the reason why the model thought the patient has a high risk, right, for heart attack. Now, whether blood pressure is correlated with an increased risk of heart attack or causal factor for an increased risk of heart attack is debatable. An elevated blood pressure may not be the real cause for an increased risk of heart attack. There could be what is known as a confounding variable, which is actually causing the elevated blood pressure, which in turn is responsible for the increased risk for heart attack. Because unless you point out the cost to the patient won't know what is to be addressed. If you simply say elevated blood pressure, maybe the patient still won't know what to do to bring the blood pressure down, right? So is there a fundamental cause underlying the blood pressure, which needs to be considered, is something important to look at. So, I mean, there are plenty of examples online on the difference between causation and correlation. Here is a simple statistical example. These are plots of ice cream sales and shark attacks in a certain Bay Area around the world. And you can see that both of them peak in the summer. Now, which means summer or late summer along those months. Which means if you now build a machine learning model where you had both these variables as part of your system, one of them, let's say, was part of the input, one of them, let's say, was part of the output. You're now going to say that an increase in ice cream sales results in increase in shark attacks. Now, this has nothing causal to it. This is purely correlational. But then a machine learning model will do whatever it takes in data to make the prediction. It doesn't worry about separating what could be a causal influence from a correlational influence. But the moment you start talking about explainability, then causal becomes very, very important. You want to know what caused the problem so that you can fix the underlying cause. Merely what is correlated, right? So for example, if based on such a machine learning model, somebody advised a local government saying that you're having high shark attacks because you're selling a lot of ice creams. This makes no purpose. It doesn't help the government in any way. Just because they are correlated doesn't mean that one becomes the cause for the other. Then question becomes, how do you isolate these kinds of causal relationships and give useful explanations in practice from machine learning models? So one of the core examples for fundamentals of causality. So causal inference was largely spearheaded by a person called Julia Pearl. He won the Turing Award for this work in causal inference about in 2013-14, if I'm right. And he has a tremendous framework performing causal inference. It's in some sense an extension of basic probability. And here is a simple example of why causal inference is required. This is popularly known as the Simpson's paradox. Right? Let's consider this setting where there were a couple of vaccines, let's assume, that was available to treat COVID-19. Right? So let's take a contemporary example that we perhaps have not forgotten yet. So let's assume that there are two treatments. There's vaccine A and vaccine B. Let's say vaccine A is 0, vaccine B is 1. Let's assume that a patient's condition could be mild or severe, 0 or 1. And based on that, and based on the vaccine, let's say the outcome for that patient was alive or dead, 0 or 1. Right? I hope you agree with me that this is kind of data that we could have collected in the last couple of years as we went through the COVID pandemic. Now, let's assume that this is the data that's given to us after collection. And we find that in case of vaccine A, 240 of 1,500 people who received the vaccine had high mortality, which means they passed away. Whereas for vaccine B, 105 of 550 people, that's 19%, actually had mortality or they passed away. Now, if I had to ask you a question as to what do you think, right? Is which of these vaccines would you take based on these statistics? Right? Let's say I asked this question, right? It's a simple answer to perhaps say that you should perhaps go for vaccine A, right? It has the lower mortality rate. So if somebody showed me this and put this out in a newspaper, then we would all spread the news that go for vaccine A, it has lower mortality rate. If somebody asks you, you would say, it seems safer, go for vaccine A, right? Now, the story is not complete because unfortunately, this only talks about treatment and outcome, and it doesn't talk about what is known as the confounder variable here, which is the patient condition itself. And when we put that statistics into the mix, here are the numbers that come out. We notice that in case of vaccine A, among patients who had mild symptoms, it had a 15% mortality. Among patients that had severe symptoms, it had 30% mortality. Overall, it had a 16% mortality, depending on how many mild symptom patients got exposed to the vaccine and how many severe symptom patients got exposed to the vaccine. Now, on the other hand, the vaccine B got 10% mortality on mild condition patients and 20% mortality on severe condition patients, leading to an overall mortality of 19% based on the split of how many patients with severe symptoms took vaccine B versus how many patients with mild symptoms. Now, this is intriguing, right? Because now you notice, if you look at the total mortality, vaccine A is lower than vaccine B. But then if you look at the individual mortalities, vaccine B is actually lower on both mild conditions and severe conditions. This system, this setup is known as the Simpson's paradox. On both conditions, mortality of vaccine B is lower, but the overall mortality of vaccine A is lower. Okay, why? I'd have loved for this to be more interactive, and hopefully I was there in person. But for the moment, let me give out the answer. The reason is more mild patients took vaccine A. Right? Just because of the imbalance of how many mild patients took vaccine A versus how many severe patients took vaccine A, because of that, the overall mortality of vaccine A went down. If you looked at this carefully, along with the details for the confounder variable, it's vaccine B that's actually the safer choice. In fact, if I now asked which treatment to choose, it still depends. It actually depends on what is known as the causal graph of how these variables are interlinked. If you had a causal graph such as this, where the condition influenced the treatment and the outcome, then you should go for treatment B, right? Because it's very clear that treatment B or vaccine B gave a lower mortality rate under both mild and severe conditions. On the other hand, if your treatment influenced the condition did not influence the treatment, and the condition influenced the outcome, you can as well go for vaccine A. Okay, now it depends on how the variables are actually connected to each other, or what is the real causal graph behind the data. And according to that, you can actually make a prediction. Right? So this should convince you that often just looking at data as it is and making a predictive model, one could view this from a pure statistical perspective, or one could view building a machine learning model on such a statistic, which would also predict that vaccine A is the right choice for many patients. Now, one could just depend on data and make such machine learning models. But clearly, if we had access to the causal graph and understood the causal relationships between the variables, we'd actually be able to make better predictions, better outcomes. Why is that important? Because AI and machine learning models are being deployed in risk-sensitive settings where it's the lives of people or property of people that actually becomes at stake. That's one strong motivation for why we need to consider causality in deployment of AI machine learning models in general. So causality in machine learning can be used at several levels. Judea Pearl, as I said, he's considered as the founding father of causal inference in recent years. He has a couple of very nice books where he presents this as a hierarchy of how one can integrate causality into AI and machine learning. Right? What we have today as machine learning and data science in the broader practice world is only level 1. which we refer to as association or estimating the conditional probability, right? So for all of machine learning models, especially supervised learning, we are often trying to just estimate what is P of y given x. Given an x, what's the conditional probability of a certain class label? Right? So what is the activity that's involved here? You're seeing your data and trying to estimate your conditional probability, right? So the typical kind of questions the system answers is, how would seeing X change my belief in Y? Okay, that's what measuring conditional probability effectively turns out to in terms of an intuitive question. Now, there can be a higher level of analysis, which is called intervention. Intervention is not just seeing your data and deciding, but intervening and asking a question, right? I do see this, I do see the data. Okay, I see that a lot of patients with a certain vaccine have had a lower mortality rate. I may want to intervene and see, for that patient, instead of vaccine A, if I had given vaccine B, what would have happened to their mortality? Okay, this is known as intervention, right? I want to intervene and see what happens. This is introduced as a new system of probability called denoted by what is known as do calculus, which is given as P of y given do of x comma z. Do denotes that it's not just an observed x, it's not just an observed variable there, it's an intervened variable, right? So you're actually intervening on a variable and saying that this is the value that I'm going to set it to. Whatever be the observed value doesn't matter. Let me see what the output now could be. What could be the conditional probability now? What is the question that we're trying to answer here? What if I do X? What happens? Not just see what's available, not just what observed. Not if I toss a coin, I get head is one way of looking at it. What if I toss a coin and I keep getting tail all the time? Right? So that's what I'm trying to ask here, intervention. That closely relates to the next level of reasoning, which is known as counterfactuals, which is, can I imagine what would happen if I had a different set of inputs? P of yx given x prime y prime, right? So P of y given x is what I see currently. Can I imagine a different future? So can I say that if I had taken this vaccine, what would I have looked at 6 months down the line? That would really help me, right? That would help a lot of people in the real world today. Right? If I know if the doctor prescribes a drug to me, it's based on a mental prediction model that they have in their mind, right? They've seen a lot of patients, they have experience, and now they are looking at all of these data points in their past. They've built a mental model, and now they are saying that for this patient, this is the drug that could actually help solve the problem. Now, what would be interesting is if we could envision the patient, go back and see, if I gave this drug, let's go look at their river 6 months later. Unfortunately, we cannot peek into the future, but counterfactuals is about imagination. While a lot of physical manifestations we cannot see, as a human mind and brain, we can imagine. How do we make AI and machine learning models imagine data is what counterfactuals is about. And a causal framework also allows us to intervene as well as get counterfactuals as part of its fundamental framework. This is what makes it different from AI and machine learning. So just to rephrase, AI and machine learning as we see it today is at level 1. We are only trying to estimate conditional probabilities. What we really want to do with a causal framework is go towards these aspects of reasoning and abstraction, which could greatly enrich the AI deployment scenario around the world today. Where can such use of causality be relevant in machine learning today? As I mentioned, it could be used for explainability. It could be used to generate counterfactuals and understand the future or understand alternate worlds or alternate universes. It could be useful in disentangled representation learning, causal effect identification, causal discovery, making models fair, right? How do you make models fair? If I ensure that, for example, if I now ensured that while giving a loan, I ensured that gender is never a cause, then I've become fair in terms of gender, right? So that's the way causal can be integrated into fairness of AI machine learning models. It can also be used for domain generalization, transfer learning, so on and so forth, right? So plenty of different applications, many of them yet to be explored and understood in detail at this point in time. Okay, so with that problem setup, I know I'm half an hour into the talk. Maybe I'll try to stop a few minutes ahead of time, so there'll be some time for questions. Maybe the next 20-25 minutes, what I'll try to do is to talk about a couple of recent works in this context, in the notion of causality in explainable AI, and go into some details. So hopefully, while I give a breadth perspective of what this means over the last 20-25 minutes, I'll try to go into the depth on one of these topics in the next 20-25 minutes. Okay. So there are two questions we focused on in a couple of our recent papers. In one of our earlier papers in 2019, we tried to ask the question, if you have a trained neural network model, you've already trained it, you've already deployed it, right? So you deployed it for any problem that you could think of, predicting spam in an email or predicting risk of heart attack in a hospital. Can I find out what kind of causal relationships it learned between input and output? Okay, I want to understand what kind of causal relationships a neural network learned. Okay, this work was in ICML of 2019. And more recently, we also asked a complementary question. The complementary question is, if I already had access to some known causal relationships, I'm building a machine learning model for a hospital, for a doctor, and the doctor tells me that, you know what, why are you simply taking data and building a model? I'll sit with you and tell you, clinical literature over the last many decades tells me that this variable influences that variable. I know it, right? We have studied many, we have conducted many clinical trials in the last 2-3 decades. I know it. Why don't you integrate this into your machine learning model? Sadly, we don't have that at this point in time, right? Machine learning models, you just dump data, they learn what they need to learn to solve that problem. But how do you integrate causal priors into these machine learning models is a more recent work. So that's the complementary problem. In one problem, you have a trained network model. How do you understand what causal relationships it learned? On the other side, if you had causal relationships, how do you ensure that the neural network learns them while training? This is a complementary problem, which was presented at ICML earlier this year. ICML is a very popular top-tier conference in machine learning. So let me talk about each of these works over the next 15 to 20 minutes. Right, so the first work, as I mentioned, is called Causal Attributions in Neural Networks. This was joint work with students Aditya, Piyushi, and Anirban. So to the best of our knowledge, this was the first such effort for integrating causality into attribution or explanations in neural networks. So the first thing that we'll start with is, how do you define causal effect at all in particular, right? So in general, causal effect could be defined as, if X was a binary variable, then causal effect is expectation of Y given that you intervene and set X to 1 minus expectation of Y given that you intervene and set X to 0. Very simple, right? So that's your standard, that's your causal effect. If you had continuous variables, that becomes a little tricky because you don't know what the baseline value of X could be. So we define it as X as expectation of Y given that you intervene and set a particular dimension of X to alpha minus some baseline value of that dimension. If Xi was blood pressure, your baseline Xi could be 120 by 80. You want to see what are the different outcomes when the blood pressure was 120 by 80. And the first term would be what are the different outcomes of different patients when the blood pressure was a certain value, maybe 200 by 100 or something like that, right? So, and because a baseline may not be well defined for all variables, for blood pressure, we know what is standard values. For many other variables, there may be no standard values per se, right? Forget the medical domain, could be even in other domains, there may be no standard values. Then what do? We simply take the expectation over the first term here and take an expectation over it, and we call that as the baseline itself, right? So that makes a simple reference value that we have for the causal effect. And by attribution, what we mean in this context is the effect of an input feature on the prediction function's output, right? I hope you agree with me that that relates to explainability. How do you explain that a certain input feature affected the output that you're trying to study in a model? This is inherently a causal question, right? So you want to know which input caused a certain outcome, because then only you could take any actions on changing the outcome if required. However, existing attribution methods are largely gradient based, and gradient is also defined by correlations. It's a local approximation because you're looking at, if you perturbed an input locally, how would the output change? So that's your first principles definition of gradient. The other kinds of methods people have used for attribution is to use surrogate models, where while to explain the decision of a certain machine learning model, you use another machine learning model to be able to learn the relationship between input and output and make it predict that attribution value. Both of these are driven by correlations. The question is now, how do you get the causal effect between input and output? One could view a gradient-based approach to getting attribution as computing what is called individual causal effect. Right? By individual causal effect, we mean that you take a particular xi, one of the dimensions of x, set it to alpha, and now if you change you set it to alpha and then you later change it to ui plus epsilon. Right? So initially you set at a particular u, and then you change it to ui plus epsilon and see what happens. Okay, that's your first principles definition of gradient. Unfortunately, these kinds of methods are sensitive. They only measure individual causal effect, not average causal effect, and cannot give global attributions. So how do you measure average causal effect as attribution in a trained neural network is what we investigated. To do that investigation, we began with defining what is called as a structural causal model. Structural causal model is like the fundamental framework for understanding causality with any kind of a data setup. We assume that any data that we see in the real world, right? So any data that we see in the real world comes from some structural causal model, right? So there are some variables that are generating the data. Right? So for example, if you take a picture that we see today, the picture is a projection of a certain scene on the lens of a camera, right? On the sensor, whatever the sensor be of that camera. Now, what was that causal variables that generated in the picture? Maybe a person, maybe the light, maybe the texture, many other things that actually caused that particular picture to be taken. We assume that every data in the real world has such a structural causal model. It's just that we don't know what that is in most cases. Right? We define the structural causal model to be made up of 4 variables: X, a set of endogenous variables, which are the variables that we are interested in; U, a set of exogenous variables that could be noise variables and other variables that are impacting the generation; F is a set of causal functions that connect the connections between these variables, assuming that x1 is connected to x2 in among these variables. Then what is that function that connects x1 to x2? Right? We assume that there is a function, but we don't know that function. Right? And finally, the distribution of the exogenous variables itself. Now, this is a standard definition of a structural causal model. So we begin by noting that you could look at a neural network also as a structural causal model. Right? So once you have learned a neural network, you could now say that all the input variables that you have, right? All the input variables that you have, this is the input layer, this is the output layer. So all the input variables that you have are like endogenous variables. All the different layers are like endogenous variables. Then you have some noise which you cannot control. F1 to Fn are the causal functions that take you from one input variable to one output variable, right? So those are the different variables that we have. And PU is just the distribution of the exogenous variables. Now we show that because we are interested only in input and output of the neural network, right? So we're not interested in the intermediate layers of the neural network. We are only interested in the causal effect of an input variable on the output variable. That's what we're interested in. So we show that one can marginalize out all of the intermediate variables. And this structural causal model boils down to something simpler, where you only need to look at the first layer and the last layer in the endogenous variables of your structural causal model. And F prime are the new causal functions that connect the input variables with the output variables. Now, inside this structural causal model, we once again look at the average causal effect as the expectation of y, given that you intervene and set a value of xi to alpha, minus the baseline value when xi assumes a certain reference value. How do you define the baseline? As I said, you could either get it from domain knowledge, or in our case, if you don't have the baseline value for that variable from domain knowledge, we simply take the expectation of expectations and assume that that's a fairly representative baseline value in this kind of a scenario. Now, the challenge in causality is how do you compute this quantity, right? This is known as an interventional expectation, just not an expectation. It's an interventional expectation because you're intervening on a certain variable in your system and seeing how would the outputs change if I intervene on that variable. Now, how do you compute this becomes a challenge. So what we begin with is to say that by first principles, this interventional expectation can be defined as an integral. And we define a few quantities here, where mu j is the interventional mean of each of the variables in your input. Mu is the vector of all of those interventional dimension-wise means. Okay. And then we look at the Taylor series expansion of one of these causal functions. Right? As I mentioned in the previous slide, each of these f primes are actually the causal functions that we want to estimate. F prime is not a gradient, it's just the causal function. Okay. So we want to estimate that causal function on the input layer. L1 is the input layer. So by Taylor series, we know we can write it as fy prime mu, which is mu is the mean input layer, plus the first degree expansion of Taylor series and the second degree expansion of Taylor series. Okay. Now we notice here that if you marginalize over all of your other input neurons and intervene on xi to be alpha, okay, the first thing you'll notice is that this term would go to 0, because when you take the expectation of it, you'll end up L1 minus mu will become mu minus mu, it will become 0. You'll actually be left with the first term and the last term, assuming that you intervene and set your xi to be alpha. Okay, that's what you'll be left with. Now we show now, so that's what we have so far from the Taylor series expansion. So now we can, it's trivial to understand that if you have an input neuron of a neural network, okay, if you intervene on it, you deseparate it from other input neurons. It becomes independent from the other input neurons, because the moment you intervene, you are setting the value, right? It becomes independent of the other variables in the input layer. And because that happens, you can show that Pxj, given that you intervene on another variable do of xi equal to alpha, is Pxj itself. And using this, we show that all these interventional means and covariances that we have in this Taylor series expansion actually become observational means and covariances, which can be obtained from data directly. Right? Observational means and covariances are simply means and covariances that you compute from your data. You can actually get it directly from your data. So this is beautiful because we wanted a causal analysis. A causal analysis requires us to compute an interventional expectation, but we find that the interventional expectation, because of the setup that we have, boils down to computing some observational means and covariances, which makes our average causal effect possible to compute. And for our baseline, we use some causal regressors to estimate the causal effect, this first value for many different data points, and then use that regressor to predict this particular value over multiple iterations of xi. This is more an implementation hack that we do to actually make this computable. One last aspect of our framework is that we do have a Hessian here in our Taylor series expansion. Right? It's after all a second degree term. So which means we have a Hessian here as part of the Taylor series expansion, and computing the Hessian in a neural network can be very computationally intensive. So we use some linear algebra trick here. We notice that we are actually not interested in the Hessian, but we are interested in a product of the Hessian with vectors from a covariance matrix. That's what we end up wanting. And we show that just doing some linear algebra juggling around, we actually show that you could estimate this product of the Hessian with vectors of the covariance matrix using 3 forward passes of the neural network. Right? We show that limit epsilon tending to 0, this becomes equivalent to this product of the Hessian with a vector of the covariance matrix. And that comes from taking a certain input, forwarding it through the neural network, getting an output, slightly perturbing the input, getting another output, and taking the original mean and getting the output of the neural network. And now adding and subtracting them actually becomes the Hessian vector product. Right? So this makes our method actually doable and computable in practice. We show that a similar thing can also be done with recurrent neural networks and handling time series data also as part of our framework. Now to just show you one result, right? So here is a result on a very popular data set called IRIS. In IRIS dataset, we actually analyze data class-wise. Iris setosa is a class, iris versicolor is a class. And we are trying to see the causal effect of each variable of the iris dataset on this class variable called the iris setosa. What you see here are different interventional values and the corresponding causal effect, which is shown as graph for different input variables. Now we do this for different classes. And what is interesting, if you observe carefully here, if you just look at the yellow regions in the 3 cases, it shows that for the iris setosa class, you notice that the petal width here and petal length have a high value for initial interventions, a high causal effect for interventions in a middle range, and a high causal effect for Iris virginica in the higher range. Now, when you actually build a decision tree independently on the same data, we notice that a very similar pattern emerges in the decision tree also, right? When petal width is less than 0.29, the decision tree says Iris setosa class, which resembles the causal effect that we actually get in the first graph here, and so on and so forth for the Iris versicolor class and the Iris virginica class. Okay, so this is a validation of the causal effect being useful in practice as validated by a decision tree that we independently built. We also show using some synthetic data that our results can also hold on time series data. And more interestingly, we actually validate this on a sensitive application on some aircraft data on whether an aircraft had a bad landing or a good landing. Okay, this was a collaboration that was done with Honeywell, and where we took a lot of public data that's available on the NASA Dashlink data set. It's publicly available. And it's also known whether a particular flight had a bad landing or a good landing. Okay, so what you see as different images here are the last 1,000 feet of landing is shown in time along the x-axis. Along the y-axis are the different variables that we needed to consider based on inputs from aircraft experts. And the color actually shows red for high causal effect and blue for low causal effect. What we find is that for a flight which had a bad landing, our method actually shows a high causal effect for pitch and roll. Whereas for a normal flight, the causal effect is all over the space, right? It doesn't have a specific pattern. But for a competing method, we find that it doesn't make any difference between a normal flight or an anomalous flight in terms of understanding the effect behind why a flight had a bad landing and why a flight had a good landing. Okay, so and we actually verified this with aircraft experts and the flight data recorder report and found that this actually matches the experts' understanding of the landing also. Why is this important? Why were we studying this problem? We received some requirements from the company that as pilots are in the air, they often would like to know whether the flight may land badly. And if it may land badly, what could be a cause for it so that they can fix it before the landing rather than have to have a bad landing. Okay, that was the context of this particular work here. We also showed that our method actually satisfies several axioms of attribution, such as completeness, sensitivity, implementation invariance, symmetry preserving, so on and so forth. If you're more interested in this, you can go ahead and look at our paper on arXiv, or the code is also publicly available if you'd like to use it for any of the applications that you're interested in. Maybe the last 7 or 8 minutes, let me probably also talk about the converse problem that I mentioned, which was presented a couple of months ago at ICML 2022. This is joint work with students Gautam Srinivas and collaborator Amit Sharma from Microsoft Research. And in this context, what we were trying to ask is, if we had causal explanations already with us, how do you ensure that a neural network respects them and trains them? Right? So for example, a doctor tells me that I know that if the patient took a certain drug 5 years ago, it could have caused maybe a risk for cancer, right? Or risk for heart attack, something like that, right? So they know it from clinical studies. Now, machine learning models that we see today are all data dependent, right? You only learn from data. Now, how do you ensure that this domain knowledge that we have from the past, from experts, is integrated into machine learning models that we build is perhaps the core focus of this particular effort. And what we try to do is what you see here, that in the real world, you could have multiple kinds of causal domain priors. Right? It's possible that there are some monotonic relationships between input and output that is known. For example, we know that if we want to use machine learning to predict whether a student will get admitted to a university or not, students' test score, maybe a JE score or a CAT score, a GMAT score, on admission obviously increases in a monotonic way. Higher the score, higher the chances of admission. It's monotonic, right? Or you could have fairness constraints where you say that skin color should not have an effect on whether you say somebody is beautiful, or race should not have an effect in a bank's loan approval model. Or similarly, you could also have U-shaped curves between input and output from randomized controlled trials, or J-shaped relationship between alcohol and heart disease that are all known and understood from literature. How do you ensure that these kinds of causal priors are respected by a neural network is what we try to do in this particular work. And our overall idea is something like this. We call a method called CREDO. CREDO stands for causal regularization with domain priors. If we knew a domain prior and a shape for that function that connects input to output, the question that we try to ask is, how do you ensure that the causal effect that we obtained using our previous work on this neural network actually matches this domain prior? Okay, that's the core idea of our approach. And we show in our work that we can actually regularize for three kinds of causal effects. Something called a controlled direct effect, a natural direct effect, and a total causal effect. Right? I'm not going to describe each of these in this particular talk, but causal effects can be of different kinds, whether a variable directly influences another variable, or whether a variable influences another variable indirectly through a third variable. Right? So then, depending on that, you can have a direct effect, indirect effect, total effect, which is the combination of direct and indirect, so on and so forth. We show in this work that we can actually make a neural network respect direct effect and total effect in our particular work. How do we do that? I'm not going to go through the definitions and the theorems, but very quickly to speak, we formally define what controlled direct effect in a neural network could mean. We similarly show that such a direct effect is identifiable in a neural network. By identifiable, we mean that you can compute it in practice. That's what identifiability really means. We show that formally that such a direct effect can actually be identifiable in a neural network. And okay, this is the formal proof, very simple proof, but these propositions actually have proofs to show that these kind of causal effects are identifiable. And then we come up with a simple method where the implementation of the method is very, very simple. Right? So obviously the math tells us that this is possible. The implementation gives us a very simple implementation of this idea, where we say that the gradients of the neural network that we learn, F is the neural network that we learn, must match the G's or the domain priors that we are given. Right? So not the G's, the gradients of the domain priors that we are given. Very, very simple. We say that if somebody gives us a domain prior of a variable connecting to an output, we should ensure that the gradient of the neural network should match the gradient of the domain prior. Very simple, but we actually show that doing it this way satisfies all the properties that we came up with and makes the causal effects identifiable. And hence we can check whether the causal effect that we are learning through this procedure matches the causal effect that we're really looking for in a neural network. And using this, we are actually able to show our results on multiple kind of data sets. So just to take one of these graphs and explain, Compass is a data set that studies racism. And what we do here is to look at the ground truth. The ground truth says that being African American should not have an impact on whether somebody could be a criminal or not. Right? So that's what the red line says. So you want it to have zero impact on the outcome. If you simply train a model using standard machine learning, which is called ERM, empirical risk minimization, which is the green curve, shows that that's not actually true. As you increase the amount of African American in the data set, there is a higher risk on a person being classified as a criminal. That's what the green curve shows. And we show that using our method, which is the blue curve, we are actually able to control that and bring it closer to how we want it to be, where we want a person being African American not having a direct causal effect on a person being branded a criminal. Right? So we show several other graphs with several other kinds of ground truth variables. We show that it need not be that the ground truth should be flat. If you take monotonic variables, U-shaped variables, and all of those variables, matching the local gradients actually achieves the desired causal effect in a neural network using our kind of training procedure. Right? So we show our results when the causal graph is known. We show our results even when the causal graph is unknown by doing an empirical training procedure that can actually get what we want in these kinds of scenarios. If you're interested more in this work is also available on arXiv. The code should soon be available if you're interested in taking this and implementing it. Just to take a couple of minutes to conclude and talk about our other efforts. So we have been looking at several other things. I talked about a couple of things today, which is the causal efforts on causal attributions in neural networks, as well as trying to do causal regularizers at this point in time. We've also been looking at several other things, trying to come up with causally disentangled representations of data, coming up with a data set for causal representation learning. Unfortunately, these days, you don't have a data set to be able to study this and validate this. And we've also been looking at how do you mitigate bias in machine learning models from a causal perspective. Right? So We are also interested in non-causal approaches to this, but that's perhaps beyond the scope of this talk at this point. But I'll be happy to interact with anybody who's interested in these directions also. Just to conclude in terms of what next, right? What can somebody do in this space going forward? Right? There are multiple extensions of what we have done ourselves. One is, how can you estimate causal attributions when your inputs are not independent? Right? So that's something that we did not study in our work. We assumed causal independence between the variables. What if your input variables were actually causally dependent? Right? So then how do you measure causal attributions is an interesting extension of our work that can be done. And finally, any causal approach, the fundamental limitation to practice is computational overhead. Because by definition of causality, if you saw the very first definition of causal effect that we came up with, there is an expectation term that needs to compute if I intervene and set a particular variable to a specific value, how does the expectation of another variable change? And the only way you can measure that is to allow all other variables that you did not intervene on to take all possible values and get the expectation over all of them. And that is inherently computationally intensive. So how do you make these more efficient and effective? I think is a very important problem to solve, because without that, this wouldn't translate to practice. Trying to use offline computations, clustering methods, or hacks such as KD trees, locality sensitive hashing, so on and so forth, could actually significantly improve the implementation of these methods in practice. What can we do going forward as a community? Trying to learn disentangled generative processes and mechanisms. Can we understand the true causal generative process that generated the data itself? If we could learn that, nothing like it. Right? So that's the best way we could build models, rather than simply build models based on the data surface that we see. We'd like to know what is behind the data to be able to make predictions more reliably. How do you perform causal representation learning? How do you do disentanglement and counterfactual generation when your variables could be heavily confounded? You have some variables, but you realize that what you're seeing is not the truth. There's some other third variable behind the scenes that is causing these variables to have these values. How do you find which of the variables is a confounder? How do you disentangle them and generate counterfactuals under these settings becomes important. And also more generally, aligning causal with compositional representation learning would be a very interesting direction to look forward. With that, I'll stop here for this talk, with acknowledgements to all my student co-authors and collaborators, as well as all our funding agencies which have kindly supported our research over the years. I'll be happy to take questions in the remaining time, or you can feel free to email me and I will be happy to respond to any questions also. Thank you again for the invitation, and I hope this talk was of some relevance and use to all of you, and at least gave some new perspectives too. I'll be very happy to take questions at this point in time. Thank you. Thank you again. Yes, I think there's a question from Patrizio. Please go ahead.
Good morning, and thank you for your beautiful presentation. I have kind of a philosophical question.
Sure,
does the concept of causality depend on the interventional word we consider? I mean, when we change the parameter space, when we move around, can it happen that the concept of causality changes? So that's something that is casual in some word is no more casual in some other word.
Sure. I think we are talking about all of this within the context of a certain distribution. That's the overall context. But by intervention, what we mean is, if we'd like to, let me put it this way. So when we intervene, to find the causal effect, we have to take the expectation of some other variable, assuming that we set one variable to a certain value. And when we do that, we have to now marginalize over all other variables in a certain distribution. Now, in a sense, now that distribution defines what the causal effect would be. If that distribution changes, then absolutely yes, the causal effect will change. So for example, the causal effect of blood pressure on a risk of heart attack may be different in India and could be different in Italy or in Europe or any other country. So if that distribution on which we are measuring these quantities changes, obviously, yes, the causal effect will change. But that may not be wrong, because that's what we are trying to study. We are trying to study within, let's say I had a data universe from India. I would want to know what's the causal effect of blood pressure on the risk of heart attack within Indian context. That's what I'm interested in. So now to do that, what I would do is I would fix the blood pressure to a certain value and allow all the other values to change in arbitrary manners based on the distribution that I have. But that changing of values depends on that distribution. So you're right, that is contingent on the distribution, but it makes sense for that distribution. Did I answer the question?
Yeah. Thank you so much.
Thank you. Thank you for your question. Yes. Any other questions?
Don't have any queries, we can move forward. So thank you, Vineet sir, for giving us a talk on socially relevant aspects of explainable AI as well as machine learning. So the goal towards organic lifelong learning of robust explainable models by your research group be a great success and be a good to the society. So thank you once again, sir.
Thank you. Thank you very much for having me again. Thank you.
So our next talk will be by 11:15 a.m. by Vijay Natarajan on topological descriptors and scalar field comparison. So participants, please fill the feedback form that is given in the chat box for this session and kindly join by 11:15 a.m. for the next talk. Thank you.
Thank you, Professor Vineet.
Thank you very much, Dr. Vinod, again for the invite.
Yeah.